What up, guys? Today we're covering chapter 6, the study guide. I'm gonna cover everything that I found while studying this. We're gonna do a couple problems and we're gonna try to remember everything we need and get prepared for this midterm exam. But first, I want to start off with some piece of advice that I think is important for any aspect in life, any goal or objective you have in front of you. This advice not only is useful, but I think it's something we all have to go through unless you are a very, very, very lucky individual. And that is, you gotta put in the work, bro. Nobody is gonna force feed you this information. There's no magical series of words that I can say such that you will then be able to solve all of these problems that you see in this chapter with zero practice. You have to put in the time. But it doesn't mean you have to dedicate your entire life to this. You could literally just check this 30 minutes. What I have in front of you is me studying for 30 minutes and then trying to solve a problem for 30 minutes. That's 1 hour. You guys can do this while on the bus. You can read, you can watch videos. The important thing is, and this is the piece of advice, is you have to think of questions. You have to think of things to ask. And that is very important in science, but I think it's important in every aspect in life. Like, I don't know, let's say you're training to be an Olympian. You have to ask questions. How can I become the best Olympian? What do I have to do? What exercises should I perform? How often should I do them? Who can I ask for help? And then, depending on your niche, you will get into more and more deep questions that are going to help you out. In this scenario, we're studying classical mechanics. You're going to have questions about this shit. Please feel free to ask me. I am a resource. You guys have a device connected to the internet. That's how you're watching this video. That being said, sometimes you need a nice foundation from somebody who knows what the fuck they're talking about. So today, I'm going to go through how I studied for this chapter, and keep in mind the things that I mentioned. Keep asking questions throughout this whole thing. You have to read a problem, think about it, and then questions will come up. If you don't have any questions, just watch this video. I'm sure a few will come up. And if you still don't have questions, you can always just read the solution or ask me to do a problem. I'm always going to do a problem for you guys. Just send it to me in the comments. And keep in mind the first thing, which is you just have to do the work. Ask questions, do the work, read, and do some problems, and you're going to be chilling, guys. I did a study guide on this chapter 6, but it turns out that some of this circular motion stuff was shown to us in chapter 4. So this is me taking notes. There's 3 important equations there. It is centripetal acceleration. It is A subscript C equals V squared over R. So I've drawn a little picture right here, a particle or object undergoing circular motion. Constant uniform circular motion, as they say in the book. It has a tangential velocity here shown in red. It has a radius of its trajectory r, and it has this centripetal acceleration pointing inwards into the center. Period, capital T, is the time in seconds it takes for the object to do one complete rotation of its trajectory. In this case, it is a circle. So if that takes 1 second, it zooms around in a circle in 1 second. Then you have that in seconds, and that is equal to 2 pi r divided by v. As you can see, it depends on the radius and the velocity. And with the units, radius in meters and velocity in meters per second, you get period in seconds. So if you want to know how long it takes for something to orbit, like the Earth or something like this, you could use this equation. Also interesting, and this is probably going to help out for a question that I found later that is pretty cool. If you have the period, so how long it takes for the thing to go around, let's say the Earth goes around the sun once a year. You can figure out how many days are in a year, how many seconds are in a day, multiply those numbers and figure out how many seconds are in a year. Then you can figure out the distance between the Earth and the sun, plug that into r, and you can pull out v, which is the velocity of Earth, the tangential velocity of it orbiting the sun, and that's a pretty crazy number. We can figure this out if we're interested, but this is the importance of writing down the equations. So this is the first thing I do when I do a study guide. Next equation, angular speed omega is equal to 2 pi over the period. So this is another thing. I'm not going to talk about this one. It's another important equation. The first thing I do in study guides is just go to the back of the chapter, write down the important equations, and then scan through the whole chapter and see if I missed any equations. These are the ones that seemed most important. There was a little picture that went alongside with them, so I just wrote them. And then we are moving on to something interesting that you can do after you have written down all the equations. You gotta find some problems that are interesting. I recommend just going through the book. There's a bunch of examples. Each chapter has like 12 examples and they're perfectly solved for you. Take a screenshot of this problem, check it on your phone, and just think about it for a bit. Remember how I said think of questions. When you read this problem, you're gonna think of questions. Question number 1, how do I answer this problem? That is the first question anybody asks on a test. Or maybe it's like, how do I relax myself? How do I stop stressing about this? Read the question, Think of a problem you have, write the problem down in your notes. This is a good thing. You need to have questions. Don't stress about questions you can't answer. That is actually the most interesting thing in science. So write some questions down and screenshot some problems and put them in your study guide, because problems are important. Then I was done with the first chapter, chapter 4, where they slightly introduced circular motion, and I moved to chapter 6, which is this one over here. I forgot the name. It's like circular motion and Newton's laws or something, Newton example, something like this. And I found this other equation. The sum of all forces F equals ma subscript c. So it's literally Newton's second law, which we checked in chapter 5, but I haven't done a video on chapter 5. Sorry about that. So we're going to get back to chapter 5 sometime in the future. If you use what we learned in the first portion, the centripetal acceleration, you can plug that into Newton's second law and you can get this new equation. And I actually made a mistake here. I should have put m times v squared over r, because ac is equal to v squared over r. But Newton's second law, F equals ma, you have m times a. If I replace a with v squared over r, I have m v squared over r. And this is important. And to be honest with you, this is the only equation in this chapter. Just like how chapter 5 mostly focuses on F equals ma, it's pretty much the only equation you're going to use. You're going to see that there's a lot of different examples and different ways to attack problems. But still, the first thing I start with is writing down the equation. I also found this little interesting picture where you have an object undergoing circular motion, and then you cut the string or something like this, and you ask, where does the particle go? And it goes tangentially straight, exactly the same velocity it had at the moment the string was cut. So let's say the sun disappeared and there was nothing keeping the earth locked into the centripetal acceleration created by the sun's gravitational pull. The sun would literally just slingshot in the direction it was heading the moment the sun disappeared. Anyway, I thought this was an interesting picture. When you guys are going through the textbook and you're taking some notes or creating a study sheet, study guide, just write down interesting things like this, little pictures, little pitfall preventions. Here's a pitfall prevention I found interesting, check it out. And we're gonna move on. At this point, I was kind of stuck with what to do. I couldn't write down any more equations because the only equations are the ones shown here. It's 4. One of them is Newton's second law. I didn't really want to write too many problems down yet. I just wanted to break down what I had to study a little bit more. So I decided, let me go to the front of the chapter and write down the sections in this book. As you'll see, the sections have interesting names. 6.1, extending particle in uniform circular motion model. 6.2, non-uniform circular motion. 6.3, motion in accelerated frames. 6.4, motion in the presence of resistive forces. So this is interesting, and it is actually very cool because it splits problems into 4 different categories. And this is going to be very helpful when we take screenshots of the problems that we're going to practice. As you can see, there's one equation, but the problems aren't just very easy plug and chug. You got to break stuff down, you got to use free body diagrams, and you also have to know the different types of problems there is. So here we have 4 sections with 4 unique names and 4 different kinds of problems. So now I'm going to go through the book and screenshot problems one by one throughout each section. Maybe I'm going to go one section at a time. Maybe I'm going to be like, you know what, let me cover the whole chapter 6 today, screenshot all the problems, and then throughout the week I'm just going to look at them, or in my homework I'm going to practice them and refer back to the problems in the book. Keep in mind, the examples in the book are already solved. You have full solutions and full explanations to those problems, and they're amazing toy problems. In physics we call it a toy problem because you learn about this problem and then you can use that to apply to other problems like a toy. So I wrote this down and that completes my equation sheet. It is very, very barren. I also circled these in different colors because I don't know, I like colors. I might associate different problems with different colors. It's a good way to remember things. And that's pretty much it, guys. Like, look at this equation sheet. Very, very short. It was done probably in like 30 minutes. Let's be real. Most of it was just looking through the book. This, if I know what to write down here, I can write this down in like less than a minute. 2 screenshots of a problem, 4 equations, 2 pictures, maybe 3 pictures, and literally the titles of the sections in the book. That's all I did, guys. This is what you can do as well. But if you're more interested, let's say you're reading through the book and you find something interesting, feel free to read it. You are not going to get hurt if you read this thing. You could read it, find something interesting, and have a question that you think about that it might be kind of a cool icebreaker with somebody. Yo, did you know that circles moving and objects moving in circles do cool things? We got centripetal acceleration. You can make a friend this way. But okay, let's get back to business. What do we do when we don't have anything to do? Just find a problem and start working on it. So here I have a problem. It was an example in the book. We started off with a hockey puck or something attached to a string. The string was 1.5 meters long. The hockey puck was moving in a flat horizontal circle as shown here. Imagine it's on a tabletop. It has a mass of 0.500 kilograms. And what the problem tells us is the cord has a maximum strength of 50 newtons. 50.0 if you care about significant figures. What it's asking us to do is find the maximum velocity before the cord breaks. So what do we do here? I mean, let's just put the main equation that we learned about in this chapter. Centripetal acceleration is equal to v squared over r. If you know that this equation was introduced in this chapter, it might instantly spring up to you to just write it down because it might be useful. Then I'm like, okay, here we got a max speed v squared. This is the velocity of some object undergoing centripetal acceleration. And boom, we have the radius there, 1.5 meters too. This is looking great. Then I was like, okay, we have F equals ma. Remember, this is one of the other equations we wrote, and this acceleration here is the same centripetal acceleration from our hockey puck going in a circle. So we have a force, and we can connect that force to the force in the cord, which we know the maximum it can sustain is 50 newtons. So I'm just going to plug in 50 newtons into F, and then equals ma becomes mv squared over r. I just replace the centripetal acceleration equation into a. I get m times v squared over r. And then I can just plug some numbers in. So we have 50 newtons. This is the maximum that the cable can sustain. We got 0.500 kilograms. This is the mass of the puck. We have the radius of the centripetal acceleration, 1.5 meters. And the only unknown is the velocity, and we are interested in the velocity. So this is going to give us the max speed, because this speed is going to be the speed exactly at which 50 newtons of force is applied on the string, as per Newton's second law. We can isolate for this, square root this, but hold up, let's check the units. So on the left side we have v squared. V, normally we want it in units of meters per second. So I'm going to put meters per second squared equals question mark. Let's analyze the units inside here. We got the mass in kilograms on the bottom over here. And we got the newtons in newtons over here, the force that the cord is experiencing. And then here we have 1.5, which is in units of meters. So I can replace this newtons using F equals ma. 1 newton is equal to 1 kilogram per second, and on the top you have times meters, so kilogram meters per second squared actually, because it's F equals ma. Then I can replace this newton inside this equation over here, and I get kilograms times meters over second squared divided by kilograms, and then times meters at the top over there. So the meters combined, we get meters squared, we get second squared, and the kilograms cancel out. So we get meters squared per second squared is equal to meter squared per second squared. So the units check out. So we can just plug and chug over here. 50 divided by 0.5 times 1.5 in the top over there. The units are in meters per second. We already did the unit analysis, and we get 12.2. And checking in the book, since like I said, this is an example, the book has already solved it, they get 12.2 as well. Significant figures, check that out. Whatever. But this was my first go on the problem. Granted, it was a simple problem. I just threw the equations on the board, and I was like, what do we do? And I just kind of plugged and chugged and, thought about the problem a bit. If you guys are interested though, check the solution in the book. The example has its own way of doing things, and you will definitely learn something because the book explains things a different way. I solved it very quickly here. I didn't really tell you what I was doing. I just plugged some numbers into some equations. You might be interested in why things are happening, why this, why that. You might have interesting questions. The book might answer some of them, but you might not find all the answers to all your questions. So this is where you can do some extra reading if you're interested. But keep in mind, the solution to this problem is super important. You got to practice it if you don't understand it. Alright guys, I think the video has been long enough and it's getting kind of late, but I want to show you this quick zoom through. This is like 10 times speed of me going through this problem, example 6.1 in the book. I got it wrong. I was kind of fumbling throughout it, but just wanted to show it to you here in case you're interested. So like I said, most important stuff, just open the book, get grinding. Let me know if you guys have questions about specific problems, and do as many of the problems as possible. That's pretty much what I'm going to show you on this channel. As many problems as possible, as many ways and analogies of remembering things as possible, and rinse and repeat, practice, repetition, ask questions, and you should be good. Just a couple more seconds of this solution. How are you guys doing? Good. Having a good time, bro? Semester is going well. You guys are staying hydrated. You gotta exercise, bro. I didn't mention this in the video. If you get bored of doing problems, go out, do a workout, brisk walk or a little set of jumping jacks. That's all it takes. Get the blood moving. Talking to some family members is also good. Talk to a friend, talk to your teacher, talk to a new classmate you've never talked before. Be like, how you guys finding this class? How's the problems going? You guys got any interesting ways of remembering SOHCAHTOA or something like this? And you should be good, bro. Make sure to eat, get some breakfast, drink a lot of water, and I'll see you guys in the next video. Thank you for watching. Leave a comment if you have a question.